Alright, hello there. So this is Frank, Holland Lee, and today we're going to be going through one of the past midterms, and I'll go through it as if I'm doing the test, and you can kind of see my thinking process, and hopefully this helps in some way. Alright, so let's get started here. We have a proof by induction. Okay, so we draw, for the sake of having enough space, we're just going to draw this down here. Okay, so what do we have here? Let's see. First of all, you notice that this is an induction proof, and there's really three things that we know about n, at least the base case of n, and then we're going to be proving the rest of it with induction. And then we have a hint here, which we'll leave in the back of our mind. So usually if there's a hint, it's going to be the harder step, and usually the harder step is the induction proof. So let's get started here. And we have this thing here, so let m be a integer that's positive. Okay, and then next we let n be a natural number, and then assume that n is larger than or equal to 2. Okay, so and then we define a predicate because predicates often help simplify things a little bit. So this predicate is going to be Pn. Let me put this in quotes. We just put this part here. So mn plus 3 smaller than or equal to m plus 1 n. Perfect. And we just now need to define what exactly this predicate takes in and puts out. So it's going to take in a natural number, but realize that the natural number is going to be larger than or equal to 2. So we can specify this here. And then we have it outputs a true or false. Great. So let's do the base case. All right. So we want to prove here, we want to prove P of 2, and that's because we're assuming that n is going to be larger than or equal to 2. Okay, and then let's write out what this means according to our predicate. So m2 plus 3 smaller than or equal to m plus 1 n. Okay, then to prove this, we take a moment to look at this. We want to show that this part is small, this part here is smaller than or equal to this other part. So we can't really do anything with this part, but we can expand this. So whenever you can expand something, you try to. Oh, and I didn't mean to write n there, I meant to write 2. So then you can clearly see that you can expand this. So we go notice, and then we write m plus 1 squared equals, okay, this is that, and we expand it out, okay, which is equal to m squared plus 2m plus 1. Okay, and now we compare this with this up here. So now notice that m is going to be a positive integer. Positive integer means that it's not 0. So imagine if m here is 1. Well, then we're going to know that this added to this is 1, and then added to 1, that's going to be 3, so it's going to be exactly the same as before, right? Okay, so then we know that m plus 1 smaller than or equal to m squared plus 2m plus 1, since m is an integer. And you can pause the video for a second if you don't understand it, but if you write it out, you'll be able to see the truth of this. And this is equal to m plus 1 squared. So then we proved the base case. All right, and then move up a little bit here. Scoot up a little bit. All right. So the harder part, the induction step. And remember to just follow the structure. You've done induction before. This is no different. The structure will often lead you to the answer, as David would say. So we want to prove, okay, rather in the induction step, we assume, oh, okay. So we now name another variable, just because, oh, here I forgot to write let n equal 2. Okay, so since I declared n equaling 2 there, then I make a new variable, and like I'll be talking about that the same way I was talking about about n, and then we know that this is going to be larger than or equal to 2, and then we assume p of k, i.e. okay, what does that mean? That means that mk plus 3 is smaller than or equal to m plus 1 k. It's great. Alright, whoops. Okay, now we want to show pk plus 1. Alright, so then k plus 1 plus 3 smaller than or equal to m plus 1 k plus 1. Okay, that's good. Okay, so now we assume this part, and we want the other part, and now we look at the hint here. So okay, so let's say, notice that what we want to show, and then we rewrite this here. 1 more than or equal to m plus 1 k plus 1, which is equal to m plus 1 k m plus 1. Okay, so let's think about this here. So okay, so we take what we know from IH, so we know that mk plus 3 smaller than or equal to m plus 1k. Okay, and notice that there's an extra m plus 1 here, right? This is the thinking process to how to figure it out. Extra m plus 1, so then you try this. You go, okay, we multiply both sides by m plus 1. How about that? mk plus 3 smaller than or equal to plus 1k m plus 1. Okay, so already this side's covered, so then we just need to multiply out this side here and see what we get. So we get mk plus 1 plus 3m plus mk plus 3 smaller than or equal to, and then we rewrite this as k plus 1. Okay, this is good. We're doing good. Okay, so well, if you look at this, like, don't forget about what we need to show, right? We need to show this on the left hand side. Well, if we were to just take a look at this is going to be larger than this, right? So we just write mk plus 1 plus 3 smaller than or equal to mk plus 1 plus 3m plus mk plus 3, right? Which is smaller than or equal to m plus 1 to the exponent k plus 1. And pause the video and try to think about this, but this is one of the tricks that you need to use in these induction proofs. So once you understand why this works, well, you have two inequalities, so then you can just drop the middle one and rewrite this, and that's it. That's your proof. How do you like that?